for joining this talk. I'm excited to see that there are people I don't know that I want to hear about this package. So that's great. I'll be talking about a Python package that we recently released in the Quantum Thinker group together with Anton, who's here, Daniel, who's also here, and Sebastian, who I think is also around. We wanted to build a Python package that would be able to construct effective models for different kinds of projects, different kinds of Hamiltonians. And we put it together into this package called Pymablock. So today I'll be telling you which contexts we considered for this Python package, how the algorithm works, and hopefully my computer will be able to allow me to show you how it runs. Let's see. So for a little bit of context, there are several projects in our group, and many of them are about solid-state physics simulations. So we have systems that correspond to Hamiltonians, and we want to compute observables from them. And these observables go from energies to density of states. We want to compute currents. And typically to calculate these observables, we need to diagonalize the Hamiltonian and find some eigenstates and some eigenenergies so that we can compute them. However, these systems can be very large. And so finding eigenstates cannot be always a simple task. And so, for example, here I'm showing a picture of a device on which Juan was working on. Juan is another PhD student in the group, and he was simulating Majorana trijunctions. So the device you see here in the middle is a trijunction of Majoranas. These are the red, yellow, and blue circles. And in order to simulate the system, they consider a substrate, a two-dimensional electron gas, a dielectric, some gates. And so this system becomes really complicated. But in the end, what they're interested in is in studying these few low energy modes, the Majorana modes, which are about 6 eigenstates embedded in a Hamiltonian that in this case was of 20,000 by 20,000 sites. And so having a low energy representation of the system is something very convenient, because then you don't need to work with a 20,000 by 20,000 Hamiltonian, but only with a 6 by 6 one. So this is one kind of system in which we can use low energy models to reduce the complexity of the Hilbert space to something that we can understand and we can more easily compute observables from. However, the problem is that tie-binding simulations are expensive, and if you want to have more detailed simulations, these Hamiltonians can have even more than 100,000 sites, and that's very large. So if you want to diagonalize a Hamiltonian that big, it will make your computer lag. And then you may want to use, for example, potentials that vary in space. And that was the case in Juan's project, where we see that there are some gates. These are VT and VL in the figure. There's also some widths that vary in space, W and L, some angles. And so to perform a systematic study of this device, Juan had to vary all these variables, diagonalize the Hamiltonian multiple times, and this starts getting more and more expensive. And so there's also the fact that Hamiltonians depend on several parameters, but often if there's a gap, then the Hamiltonian changes slowly upon variations of these parameters. So this is a situation in which an effective model would be very useful. Are there any questions? I cannot really see your video, so I hope if you have a question, you'll unmute yourselves. Okay, so this is one situation in which solid-state simulations are expensive, but I think in general we can agree that Hamiltonians are complicated. So here I'm showing a different scenario of a superconducting circuit that we see in this figure. There are different capacitances, Josephson junctions, and these are coupled in a way that it can be represented by the bosonic Hamiltonian that I'm showing here. So at this point, I don't want you to understand how this Hamiltonian represents the system, but I want you to notice that there are 3 different bosonic operators A1, A2, and AC. Each of them spans an infinitely big Hilbert space. And so if one were to write this matrix, it'll be an infinitely big matrix. But since we're only interested in these systems to build qubits, then we know that there is a low energy subspace with which we can work. And so that is another case in which only low energy degrees of freedoms are relevant. And in order to get them, we can construct an effective model. And so in this case, while the total Hamiltonian is infinitely big and it's on the left, the effective Hamiltonian is finite, it is small, and it's also interpretable. So there are less variables, like these would be these effective omegas with these g's that are also effective expressions. And so this way one can look at the effective Hamiltonian, understand what is happening. It is, in this case, an 8x8 matrix. And so one knows that if there's two qubits that couple to each other, then other responses will vary in an analytical way with respect to what is being shown. The problem is that arriving from an expression on the left to an expression on the right means that we need to find also expressions like this one. So in this case, I'm showing some of the perturbative expansions that appear when one does this procedure. And here there's a third order in G's. This expression is long and it's cumbersome to get. So deriving this by hand requires carrying out a Schiffer-Wolff transformation, which is a systematic procedure that exists for a while, but that can be cumbersome to prone to errors, and it requires a lot of work. So these were the kind of situations that we had in mind when developing this package. And the considerations we wanted to apply then were to have an algorithm that would be able to take numerical and analytic Hamiltonians, like the ones I showed before, from type binding models, where you have 100,000 by 100,000 matrices with values in them, like numerical values, but also analytical Hamiltonians where there are some bosonic operators with some symbolic parameters, and you're interested in a symbolic representation of a low energy subspace. Then there's also that, depending on the situation, you may have multiple perturbations. So you could have electric fields, magnetic fields, strain, and several different factors, couplings that vary, and all of them will be treated as a different perturbation within this framework. And so we wanted something that will be flexible and that wouldn't be constrained. Then there's also that many times we have that the lower orders vanish or are not super interesting. And so we wanted an algorithm that would be able to go to higher order corrections without needing to recompute everything from the beginning, so that you can, for example, go and compute a third order correction. And if you realize that this one is 0, then you can use what you have already computed to get the next fourth order. And then also we want to be able to do all of this efficiently. So no more pen and paper, just a computer that works well, not like mine, and be able to get correct results from this. So even though these things are things that a Schiffer-Wolff transformation can do, it cannot do them well enough, and I will explain that later. But basically, a Schiffer-Wolff transformation is not efficient, and in order to improve on it, we need to go into the details of how Schiffer-Wolff works. So unless there are questions, I will explain how that works. Okay, so how does a Schiffer-Wolff transformation work? Well, it takes different inputs and it gives an output. And the inputs are composed of a Hamiltonian, where we treat some part as an unperturbed Hamiltonian and the rest as the perturbation. And that's what I'm showing here. So let's set the case in which the unperturbed Hamiltonian is diagonal. So then we would have a few eigenenergies on a low energy subspace. there are some other eigenenergies on a higher energy subspace so that they are separated by a gap. And then we added perturbations that couples these subspace. So these are some 6x6 matrices where all these red and blue values mean positive and negative values. So there's some positive and negative eigenenergies. They are coupled by the perturbation. And the result that we want is a block diagonal Hamiltonian so that the different blocks are decoupled. So there's here a white space, there's a zero coupling. And so this smaller block we call the effective Hamiltonian. And that is a pictorial way of imagining what a Schiffer-Wulff transformation does. So what it does is to find this unitary transformation that achieves this smaller block of the Hamiltonian. And it does so at every order. So we can always compute higher orders in the effective model by computing higher orders in the unitary transformation. And this is done in a recursive manner. So one would first solve for the first order, then the second, the third, and so on. So this is only the intuitive idea of how Schiffer-Wulff works. But let's see how we implemented our alternative algorithm. So we also constructed an iterative algorithm that takes an unperturbed Hamiltonian and a perturbation. Here, the unperturbed Hamiltonian doesn't really need to be diagonal, but I'm going to show it like two blocks on the diagonal. So we call the AA subspace the low energy one. We have a BB subspace, which is a higher energy one. They don't really need to be higher and lower energy, but we call them like that, but they need to be separated in energy. And then we add a perturbation that has here one index. So this is only one perturbation, but it has terms that are, for example, proportional to lambda. So H1 would be proportional to lambda, H2 would be proportional to lambda squared, H3 would be lambda cubed, and so on. And then there's the unitary transformation, which is also a series on lambda. And the goal is to produce an output, H tilde, that is computed as a unitary transformation on H, such that for every order of lambda, it log diagonalizes a Hamiltonian. And so the algorithm has two requirements. First, the transformation needs to be unitary, and then at every order, the off-diagonal block needs to vanish. And that sets components of the unitary matrix at every order, so that order by order, we can figure out what the effective Hamiltonian will be. Are there any questions? No? I have a question. So far, not much looks different from Schiffer-Wulff, right? So in Schiffer-Wulff, one would have here e to the s instead of u. But at least right now, it looks like it's a matter of a different notation. But actually choosing u as a series directly and not using an exponential in between allows us to get the gain in efficiency that I told you before we were looking for. So by choosing u as a series directly, we're able to construct every order of the effective Hamiltonian by only requiring a linear number of products per order. So at every new order of the effective Hamiltonian, we only require a finite extra number of matrix products, which is the most expensive part of this algorithm. So multiplying matrices, if they are 100,000 by 100,000, is really expensive. Also, if they're symbolic. But if we ensure that the number of products we need to take at every order is finite, then our algorithm only increases linearly with order and not exponentially like Schiffer-Wulff does. So this is really the part in which we gain the most efficiency. And just to give you an idea of how this looks, the unitary constraint on the transformation means we're solving an equation like I'm showing here. So here W and V are different components of U. But what matters is not how the equations look like, but rather that for every new order, there is extra two products to compute. And then the second equation, the one that enforces that the off-diagonal block vanishes, imposes a similar requirement. So if we need a new order on lambda, so that's n here, then we need to add 1, 2, 3, 4, 5, 6 new products. And we never get these nested commutators that would appear in a Shirley-Wolff transformation, which require the complexity to increase exponentially. So here, this is how we achieve the nonlinear efficiency. And then there's other improvements that we make along the way. So for example, in this expression that you see here, we see different matrix products, but we have a choice on how to make these products. And that choice is crucial because if we have a BB subspace that is huge and an AA subspace that is small, then it is convenient to multiply matrices in a way that we prioritize constructing small matrices. And that is what I'm showing here. So for example, we see there's a product between a matrix occupying the AB subspace. So that one is a rectangle. There's BB, which is the huge matrix. There's another BB, another huge matrix. And if we were to multiply BB with BB first, then we would be occupying a lot of memory and a lot of time. But if we first form a rectangle by multiplying these two first, and then the other square, then we're saving lots of time and memory. So prioritizing small matrix products is something we do by using SciPy linear operators, if you're interested. All right, so these are some of the secrets of our package. But
Can
then
I ask you a question?
Yeah.
So you have two subspaces, AA and BB. And I'm not sure if I understood, but was AA, let's say, the low energy subspace, or do both subspaces have a low and a high energy set, let's say?
Yeah, sorry, I was not very clear. So AA is low energy and BB is high energy.
Okay.
But so what matters is that they don't overlap in energy, but whether they're high or low is not important for the algorithm. It's just that typically people are interested in low energy degrees of freedom.
So, right, I see. Yeah, okay, thanks.
But the algorithm doesn't care what is high and what is low. So what matters is that they don't span the same energies, because here equation 2 is what determines the energy denominators that appear in a perturbation theory result. So in perturbation theory, you typically have responses proportional to 1 over EA minus EB, and it's equation 2 that determines that. So if they overlap in energies, this will give you something like 1 over 0, and that explodes. So the result is not perturbative anymore.
Right, that makes sense. Indeed, that's the same as normal perturbation theory. Okay, yeah, thanks.
Yeah, so the results need to match with normal, usual quasi-degenerate perturbation theory. All right. So far I explained how the algorithm works for one perturbation, but one of our goals was to be able to do this for any number of perturbations. So let me show you the generalization. Say we have a Hamiltonian that has different perturbations, I, J, and K. So not just lambda anymore, but different ones. So for I, J, and K, we can come up with alpha, beta, and gamma. And then we also have then a unitary transformation that becomes a tensor as well. There's also alpha, beta, and gamma, and we will have terms like alpha to the power of I, beta to the power of J, and gamma to the power of K. And so because these two are series, the effective Hamiltonian is also a series on alpha, beta, and gamma. And the way we have to construct this effective Hamiltonian is by also applying a recursive procedure as we increase the orders, but now in a hyperspace. So we don't need to restrict ourselves to a line anymore, but we need to start constructing in this hyperdimensional space of perturbations. So if we wanted a term that is like alpha to the power of 3 times beta to the power of 4, that is this green point here, then we would need to compute recursively all the terms that are enclosed in the rectangle under this point. And so we would start by having the unperturbed Hamiltonian at the origin, then computing first order in alpha, first order in beta, second order in alpha, alpha times beta, and so on, so that every new term requires the terms that we have already computed. So yeah, that's how we generalize the algorithm. And here there's another source of speed up, and that is that if we're interested in a specific term, so this one here, alpha cube beta fourth, then our algorithm doesn't require us to compute more terms than we need. So typically people would call this a seventh order perturbation theory because of 3 plus 4. And so a naive algorithm would compute a lot more orders. It would compute like everything that is enclosed or everything that is smaller than the diagonal here. But we can choose to compute only the orders that we want because we have them as independent perturbations and they're not all bundled together. So with that, I think I've explained the main ideas behind the algorithm and how we achieve some efficiency. But then, of course, efficiency is not everything. We also want something that people can use and that people want to use. And so we came up with an interface on how to use this package. So the first thing would be to have a Python to install Pymablock, and you can find the installation instructions in the website. By the way, we can install it and then we can import it. We can import its main function, block diagonalize. And this function is the one that interprets the Hamiltonian that you give. It can be a numerical Hamiltonian or symbolic. And then it also requires the information about the subspaces that we need to decouple, because that is a physically informed decision. But once you have this given the Hamiltonian and the different subspaces, you can ask for different orders by requesting them directly. And so up until the middle line, nothing has been computed really. It's only once you request the orders that they are computed and that the algorithm needs to start thinking. So now I would like to show how this works in a K.P model of bilayer graphene. So just as a little bit of context, on bilayer graphene, one needs to consider 2 layers of graphene on top of each other, such that there are different hoppings and couplings between these layers. And when studying a K.P model, we're interested in doing in using momentum as a perturbation around one point in the Brillouin zone, and the one we will choose for the tutorial is the K point over here. So that requires having a Bloch Hamiltonian of the tie-binding model, and then carrying out a perturbation theory using momentum Kx and Ky as a perturbation around the K point. So I'm going to switch to that. So, okay, here I'm showing you the tutorial. It's a Jupyter notebook. This one is also on the website, so if you open it, you can read it and run it if you like. But the first thing we do is to import NumPy, because that package will allow us to work with numerics. And then also SymPy, which is a Python package for symbolic computation. So SymPy will allow us to get a symbolic effective Hamiltonian for bilayer graphene, which is really cool. So we can import functions like symbols so that we can define the hoppings and the different parameters in the Hamiltonian. We can import matrix, square root, exponential, imaginary, different things. Then we can define the different symbols, and with those, we can define a Hamiltonian, and that matrix is being shown here. So as I said before, we're using 2 layers of graphene on top of one another. So we have a Bloch Hamiltonian that is a 4x4 matrix because each layer has 2 degrees of freedom. So far, so good. Or are there any questions? No? Okay. So far, so good. It doesn't look like a complicated Hamiltonian. But that's until we see that alpha depends on momentum, and it depends in a relatively ugly way. Say. So there is alpha that depends on kx and ky. There are some sine functions, some cosines. And as I said before, we're interested on the expansion around the k point. So what we're going to do is to find the subspaces of this Hamiltonian at the k point. So if you replace here that specific momenta, you'll find out that alpha becomes 0. So we're going to use alpha equals 0 and m, which is another term here, like a mass in the Hamiltonian, in order to find the eigenvectors at the k point. And this is a cheap part of the procedure because the unperturbed Hamiltonian has a lot of zeros. So if alpha is 0 and m is 0, then this one we can afford to diagonalize. And so we find 4 eigenvectors for this 4x4 matrix. The first 2 label the low energy subspace because they are all sorted. And then the last 2 columns are the high energy states.
Sorry, I have one question.
Mm-hmm.
I do thank you for the wonderful presentation. But here I think it doesn't depend on the k space. It depends it means on the mass term. So yeah, it is mandatory to put it as 0, or it is open.
No, that's open. Yeah, sorry, I was not very clear. I'm using, let's say, 3 perturbations. I'm going to use kx and ky, but also m, just to demonstrate that we can have more than 1 or 2. But it's not a requirement. Okay. Yeah.
Yes, good. Okay, thank you.
Yeah. All right, so that's when we can use the package. So we import block diagonalized from Pymablock. We call the function, and now we substitute the difficult alpha inside, the one that has all the sines and cosines. So it's a big Hamiltonian in expressions, not in size. And then we also specify the perturbative symbols, in this case, kx and ky, for the k.p expansion, and m, because we want to show how it works for more perturbations. And then also I give the eigenvectors of the low energy states and the eigenvectors of the high energy states. So these are the ones we computed here. 2 columns and then the other 2 columns. So we can run this cell. And as you can see, this doesn't take much time. And that's because we haven't computed anything yet. We just defined how this series are going to be solved. And we can see that H tilde is an object from our package. It's a block series. So it's a series of matrices that have a block structure. And we can, for example, ask for the dimension names because these blocks, well, they are actually tensors. So some of the dimensions are for momentum and the other one is for the mass. And if we want to compute a term, let's say that is first order in kx, and that has no contribution from ky and m, then we would compute it like this. So here the first 2 indices denote the 0, 0 block, so like the AA or low energy subspace. And the next 3 indices label the symbols. So the same here as the dimension names. So this one is a correction proportional to kx. And what we see is that this one is 0. So because it's 0, we return a 0 of the type of our package, and that allows, and so that means that from now on, this term is taken out of the series, so that when we need to compute all the matrices products, we immediately avoid computing products with matrices that are 0, which also saves some time. Then we can compute, for example, terms proportional to kx and ky, and that's the result that we see here. So already now we can observe how we went from a 4x4 matrix to a 2 by 2 one because our low energy subspace had 2 eigenvectors. So we can do things like this, and we can compute higher order terms as well. Let's say also proportional to mass. That one is also 0. And we can start computing terms by requesting them this way. So this one is also 0, right? It depends on the Hamiltonian that you input. And then higher orders take a little bit longer. But the terms that we already computed get cached in the series so that they are reused for the next computations. So something else that block diagonalized returns is the unitary transformation. Here I'm only asking for the first output. So that is H tilde. But if one wants a unitary transformation, you can also get it. And yeah, so the effective Hamiltonian in this case is a bit more complicated, but one can simplify it by using SymPy appropriately. So if you call something like SymPy.simplify, you can get a smaller expression. I'm not going to do it here, but we could, for example, expand, hold expand, and try to expand all the parentheses inside, and we get a smaller expression instead. So we cannot produce small expressions immediately, because how these expressions will look depend on the structure of the problem. But once you get an output, you can manipulate it in different ways and try to get something more compact. And yeah, so then I'm also going to show the rest of the tutorial, and that is how to get several different terms at the same time. So we could, for example, define some arrays that give all the terms proportional to k squared, all the terms proportional to k cubed, and define a convenient function that allows us to sum all these terms, so that then we can request something like all the mass terms, all the kinetic terms, all the mass corrections, all the cubic terms, add them together and get like an effective Hamiltonian that goes up to, I think this is third order. So I think that's what I wanted to show with the tutorial. And if people are interested, I can show others. But if, I don't know what you think.
Do you mean here expanding the expression of the alpha, which is the sum of exponential k dot r, it's the scalar product between k dot r? It means that, for example, if you set 1 or 2, it means that you go to the second order and the third order approximation.
Yeah, but on k, not on alpha.
On k.
Yeah.
Yes, on k. Yes, on k, because alpha is explicitly including k in it.
Exactly, yeah.
Okay.
Yeah, so alpha is mostly for the compact notation at the beginning, but alpha is a function of k. So, and what we're interested in is in how the Hamiltonian behaves as a function of k, not as a function of alpha.
Okay. So here, if it is the second order, it means that you go to the second neighboring. It's connecting the second neighboring.
The second order means that we get terms proportional to k squared.
Okay.
Yeah. So, for example, if you wanted something like a Dirac Hamiltonian, you would be going for first order in k.
Yes. Okay.
So that would be like requesting 1, 0, 0. This is proportional to kx, but this is 0 in this Hamiltonian. So it's a vanishing term. So that's why we need to compute higher order terms. And for example, this one is a leading term. It is in total proportional to k squared, but one component is from kx and the other one is from ky.
Fine. Yes, fine. Makes sense.
Are there any?
Yeah, I have another one. Yeah, so these eigenvectors you specified for the subspaces, they were fully numeric here. Can you also specify them while containing symbols or not?
Yeah, you can specify them containing symbols. That's not a problem. But what is a problem is getting a diagonalization of a big symbolic matrix. So if your unperturbed Hamiltonian was very big and it was symbolic, asking SymPy to diagonalize it may not give you an answer. So if you have the eigenvectors of the unperturbed Hamiltonian because they are, let's say, easy to guess, then you can use them and that's not a problem. But if you don't know what they are and you want to get them analytically, it can be really hard.
Right, I see.
So that's also the reason of why sometimes you want to do perturbation theory and analytical Hamiltonian, because if you have a very big symbolic matrix, then it's not always possible to diagonalize it. Or if it is possible, it can be really hard. So if you have a Hamiltonian that is symbolic and you need to compute the eigenvectors and it has a block structure, for example, you can make use of this block structure to compute the eigenvectors of each block and then put them all back together. But SymPy is not able to do this yet.
Right.
You can do it step by step, but yeah.
I was wondering because, for example, in Hamiltonian, I would consider we know the very simple Schrieffer-Wolff outcome. So we have a good, let's say, estimation of what those eigenvectors are for the different subspaces. And it seems overly expensive to indeed diagonalize the full Hamiltonian. So I was wondering if you could manually input those vectors because you know what they roughly are.
Yeah, that's perfectly fine. So at this stage, what block diagonalize does in this cell is to project the big Hamiltonian in this subspace, in the small subspace. So if these are few eigenvectors, then it's going to be a matrix product, and that you can do.
Okay, and what does it need the BB subspace eigenvectors for then? The high energy eigenvector?
So yeah, that depends. So the way we wrote the algorithm does not always require them. So how to say? So for example, we have different use cases, but if you never request the BB subspace of the effective Hamiltonian, then there is a series of matrix products that we will never compute because you don't want them. If you wanted them, you could ask for them by doing something like 1-1 here, and then you would need to use them. But if you don't ask, you don't have to use them.
Right, I see.
Yeah, but for example, if you had a very, very big numerical Hamiltonian, then we have an algorithm that uses K.P method. No, sorry, not K.P, KPM, like a hybrid polynomial. Oh, I forgot the polynomial kernel method. So, well, the summary, the summary is that it only requires the low energy eigenvectors, not all of the other ones. So so it depends on the input and on the sizes of the matrices and everything.
Okay, perfect. Thank you.
So I also had another tutorial prepared. I don't know if
sorry, can I also ask a question? Yeah, so do you also have a function where you can get the analytic form of the eigenstates in the end for all of these block diagonalized Hamiltonians?
Yeah, that's something you can do. Actually, the other tutorial has that. Maybe I can show.
Okay. Yeah, sure.
So the other one is the example I used in the presentation of a superconducting circuit. So that's a device over here, and this device is such that it's meant to represent 3 qubits. So there's qubit 1, there's qubit 2, and they are coupled to a floating tunable coupler. That's another qubit that helps you to couple the other two. And so what matters is that we're going to get an 8x8 Hamiltonian from this big expression. So we again import SymPy, we import Pymablock, and then here we have a second quantization function that will help us to go from second quantization Hamiltonian to a matrix. So what we can do, for example, is to define all the symbols that the Hamiltonian will require. We can define the 3 types of bosons in the Hamiltonian, and with them get something like H0, the unperturbed Hamiltonian that I'm showing here, and also HP. This is a perturbation. It has G12, G1c, and G2c, and these are 3 perturbative symbols. So once we have defined these in second quantization form, we can call a function. This one I'm not showing how the function works, but it constructs a matrix from second quantization Hamiltonian. And so with this, we can see here I've truncated the Hilbert space to an 8x8 one. So this is the unperturbed Hamiltonian, and this is the perturbation. So, all right, so what we want is to reduce the dimensionality of this. So another way to treat symbolic or numerical inputs is to label the diagonal elements on the unperturbed Hamiltonian, because it's diagonal, so we can say which ones are going to be low energy states and which ones are going to be high energy states. And that we do by specifying indices. So let's say here, indices is an array with 8 values, and it says 0, 0, 0, 0. So that means that the first 4 values here are low energy or belong to 1 subspace, and the other 4 values belong to 1. So that's the B subspace, the higher energy one. So we can, instead of giving the eigenvectors, we can give these indices. And then again, specify 3 symbolic perturbative parameters. And now we can request different orders. So this is now the low energy subspace, no perturbation. And then we can start computing first order correction on G12. Let's say this one would be second order correction in G1c, and then so on, like we did before. So yeah, we can compute different terms. We can time them. So as the terms, so this is now a third order correction proportional to G1c, G12, and G2c. And you can see how it starts growing. Now we can also compute all the corrections up to second order on each parameter. So we can also write some convenient functions. And in this case, we find that if we compute all the corrections up to second order and add them together, our Hamiltonian has a block diagonal form. So this one has here 1, 2, 3, 4 is a 2x2 block that is decoupled also from this 3x3 block. So we can indeed take this smaller block and ask now SymPy to diagonalize it and to give us the different eigenvalues of this 2x2 block. I hope that was not too fast. Do let me know if that answered your question. But we can now diagonalize this Hamiltonian because it's smaller. All right. So with that, I would like to briefly comment on how this is different from Schiffer-Wolff. So as I said before, we have a linear increase in the number of products that we need to perform instead of exponential like Schiffer-Wolff would have. And that's really because of avoiding the nested commutators that appear in Schiffer-Wolff. Then we also have an advantage in that we never need to truncate the series. So we don't compute terms that then we will need to throw away. And here in Schiffer-Wolff, typically, if you go to 5th order, you end up computing terms that go up to 10th order, and then you throw away everything higher than 5. And we don't do that. Then we have a way of treating different perturbations independently or bundling them together, whatever works best depending on the Hamiltonian. And the result is the same. So that's really cool. And if you're interested, there are other sources of speed up, like we are able to work with sparse matrices too. We use a package called mumps that is really good with big sparse Hamiltonians. So this helps when diagonalizing these huge matrices or using the KPM method. Then we also avoid products between large matrices. So that saves time at every step. We cache the lower orders to use them later. So we don't need to decide a priori which orders we want to compute. We can always ask for a little bit more. If there's a term that is 0, we remove it from the series. So we don't compute terms that we know will be 0. And we know that the effective Hamiltonian needs to be Hermitian. So we only compute half of the products that we need to compute. All right. So with that, I would like to thank you for asking questions. That was really nice. And also invite you to check out the documentation and to check out the GitLab repository. So here you can see what issues we have. You can open new ones, and we can have some discussions. Thank you.
If you allow, I might have a question regarding the K.P model. Does it avoid the doubling problem that we might have in quant? Because if we discretize, or if we use the Dirac Hamiltonian, we always might get the doubling problem. So here using the model that you have provided, does it allow to avoid that issue of doubling?
No, I don't think we can avoid that with the effective model. So
okay.
Yeah, no, I don't think yeah, I don't think so.
Okay, thank you.
Are there any other?
Yes, also if we have, for example, later on further questions, does there a forum that we might, like a quant forum, to ask questions? Is there a way to that?
Yeah, or you can also send us an email, or open an issue. So I can perhaps write my email here in chat. So if you have a question, you can write here, or I think that would be...
That's nice from you. Thank you.
Yeah, I would be happy to see what questions you have. So do share. All right, so I think we can maybe conclude the talk. I'd like to thank you all for asking questions. That was really cool. And I hope to see you using the package. Bye-bye.
Thank you for the presentation. It was very nice.
Thank you.